Today I thought I would do like a really low effort video and react to the animation versus physics video that was uploaded today. Just because like I'm not gonna say I like understand everything that's going on, but I at least want to like react to some of it and see how much that I know of what is going on. And try to like um I don't know, try to explain some of it. Hold on. Okay, there we go. So now we have the video up. So we're gonna start a little bit from the beginning. We're not gonna watch the whole video. We're just gonna skip ahead. I'm gonna skip ahead to some of like the scientific stuff and just try to like see how much of it I can understand and see how well I can explain some of it. I'm not saying that I'm a physicist at all. I just watched a lot of like crappy science YouTube, but I want to see just how much I understand of the video of the math stuff. So let's just get into it. So now we're starting with a stick man in empty space, and he's approaching the. He's just approaching nothing. I already watched this video, but I'm just gonna go back and react to some of the science stuff. Okay, so now we have a unit of measurement. We have a vector going from one dimension to the other, a one-dimensional vector, which is distance. This will tell us how far we're going over any two distances, any 2 points. Now we have a vector, so that's telling us what direction. And this is a new vector called velocity. Well, velocity is just basically how fast we're going and at what direction. So we're still in one dimension. That's a v. Now we have a unit of measurement, which is like how much distance over how much time, which is going to be changed to delta, which is basically like a way of saying for every second or for every unit of measurement of time, this much distance has changed. So it's just, yeah, there we go, 0 meters per second. So that's delta. Oh, there we go, d1, d2, displacement, yep. And that's just basically a unit of measurement saying how much distance has changed over how much time elapsed. And it's a very specific amount of time. So it's not like 1 second every 3 seconds, every 5 seconds. No, it's 1 second, 1 second, 1 second, or maybe 0.1 seconds or whatever. But delta is basically a standardized and equal unit of time and an unequal amount of distance change. So this is just calculating how much does something change over a standardized amount of time. And now we have v, which is our distance over time. And 2.5 meters a second. That's our vector in this direction, and now we're adding two vectors, so we're getting vector addition, which is you take one vector and you add another one and you add them together, and now you get a bigger vector. But because it's one-dimensional, all you're doing is you're just adding the vectors. Now when you have different angles, you're going to multiply their angles to get a completely new angle. We'll see that later. So now we have acceleration, which is basically like as you increase the vector over time, your speed velocity, the amount of distance you're traveling, increases as well. So your vector gets bigger over time. That's acceleration. I can't name the formula off the top of my head. There we go. Now we have friction. Hey, there we go. So that little like arrow in the floor is basically friction, and friction is when you displace kinetic energy into a volume. So like air, water, and in this case the floor. Your energy is being dispersed into the floor because you're making contact with the floor. So Newton's third law, or I forgot, Newton's law of inertia states that any like kinetic energy going into something has kinetic energy going back. So it's pushing against you, and you lose kinetic energy, which is demonstrated by that friction vector, which is going the opposite direction, making you lose speed. So now he's going to lose his speed, going to 0. Now I was curious, where is the gravity vector? Because if we're using friction, there is also like, force of the ground pushing up against you as you're standing on a gravitational body. So it should be on this planet, which is an analog for Earth, 9.8 meters per second squared. So I would expect to see a vector of gravity going this way, which is like this way, which is gravity, and then the counterforce to that, which is like the ground pushing up against you. And it's for every single body of matter. So like for example, like this glasses would represent one body, so as it moves this vector would go down, but then you can open these up and these become two separate vectors. So you have one vector going down, one vector going this way, one vector going this way. So I would expect to see like a crazy number of vectors where you have the ground pushing against him, air pressure pushing against him, gravity pushing against him, like 50 different lines going everywhere. But of course, they simplified it down so that it's not just a bunch of jarbled mess. They're trying to just put units of measurement and explain concepts of units. So that as we progress into crazier and crazier things down the video, we get to understand how they all come together into basically explaining all the phenomena in the video. There we go. So now we have a ball that fell down. So we have a gravity vector coming down this way. So now we're adding a second unit. We had a dimension going this way. Now we have another dimension going up and down, which is the y dimension in usual standardized mathematics. 1 kilogram. So now we have a unit of mass. Yep, there we go. An acceleration going up and down. Now we have the formula for calculating force, which is how much energy is dispersed when two bodies of physical material interact with each other. So you have a ball with no acceleration and like maybe 1 mass, and a ball of similar mass, 1 mass, and maybe like 5 acceleration. And then we can calculate how much force is put into the resting ball when the two collide. So now we have a way to multiply vectors as force, mass times acceleration. And now we have work, which is how much effort does it take to move an object as force is applied to it. There we go. So that's what we saw. That was what I was talking about. It goes up, and now we see gravity going up, and then we see gravity going down, and then the force from the Earth pushing back against the gravity, causing it to go up, which is a bounce. So now we see gravity and the force against gravity. Oh, wow. So that's the first thing. We now finally get to multiplying vectors together. So this is a big thing. It's calculating the direction of force. So how do we do that? We multiply the vectors. There we go. So here we go. Force of cosine sine. So cosine would be like the x dimension, angles for x, and sine would be angles for y. And then you multiply these vectors together and you get a new vector, which is the fi, which is like the initial vector. You multiply the initial vectors and you get your new vector, which is just the new force. And that force is a vector that is perpendicular to the two of them. So you're multiplying direction this way, and then your new direction will be perpendicular, meaning it'll be at 45 degrees. So here it's going to be a right angle. Right here it's going to be a right angle, and then the new vector will be perpendicular to us. So it'll be like at almost like a 45 degree to the angles of the ones you multiplied. And not to mention that gravity is also acting, so gravity is changing the force of the vector, changing the direction because gravity is pulling down. In empty space, if you have these two vectors cross, the empty space will be like a perfect, like if you ever use your screensaver and you have like a ball bouncing on the screen, right? It'll bounce on the corners of the screen. It'll bounce around the corners of the screen because there's no force acting on it. But when you have gravity wants it to come down. So it'll bounce, try to go down because gravity is acting on it, and then it'll bounce and gravity pulls it down to the bottom. So now we have gravity pulling it back down, and we also get units of force as it goes along. And we have the unit for friction as well. Now we're on a frictionless surface, which means that we don't have to worry about losing as much speed as on regular ground. So now we just get to see units moving perpendicular only to the force of gravity and the force of like work or inertia. Other than that, there will be no friction from the ground to slow it down. This is going to this will simplify the math a lot, because when you have friction put into the equation, it just makes the math way more difficult, But I'm over explaining friction right now, so I just want to get into the rest of the video. So now we have friction, no friction. So now we're free from having to worry about the ground being put into the equation of calculating motion. Oh, now we have rope. So the rope by itself, and this is coming from an unknown source. So I'm going to skip ahead a little bit. So now we have radii. So now we can do circles, which is really cool because now we can calculate bodies of orbit and bodies of torque. And here we go. We have L equals mass times velocity times rotation. So now we have angular momentum, and we can calculate stuff like torque, which is like how fast does something revolve, how much energy is in the revolution. And I'm not going to explain the math too much or how the formula works. I'm just explaining what it describes. And it just basically describes the motion of the circle. The force of a circle. There we go. Momentum. Precession, which is like the rotation between two like angles of axis. So you're rotating this way and you're also rotating this way. So it's like basically the two ways of rotation. You have linear momentum, which is basically like one direction of momentum. But this is angular momentum. So if it's linear, it's in one vector. If it's angular, it's going in a circle. Or it's going based off of cosine sine. So now we have a way to make rotations with our little string. And the string acts as like a way to keep it taut to the center. Alright, I'm going to skip a little ahead. So now he acted work on the object. There's another rope ahead. Okay, here we go. Here's a cool one. So now we have potential energy. This isn't going to be really like explained too much throughout the video. This is like just a small tidbit. But potential energy basically says like on resting objects, what kind of energy can we extract from them? And in this case, it's kinetic energy. So gravity will give you energy as you go down the slope, but gravity will take away your energy as you try to reach the bottommost point, which is equilibrium. So basically this ball wants to be here, but for now, the potential energy, the amount of energy that it's dispersing is going to be all this and all of this energy minus all of this energy. And it's like a calculus formula, and it converges to this point because this is where it converges to zero. But it's this energy minus this energy. So that's the total kinetic energy, potential energy in that little ball going down the hill. So for now, it overcame this slope, which means that its resting point is at the end of the slope. But if it fails to overcome the slope, then its actual resting point will be at the bottom. So he's going to try and go around. He's going to lose his kinetic energy. He gets the big rope, and now there's that rocket floating out in space. So he's going to go ahead. Oh, we have a little unit going around here. So now, yep, there we go. We go into torque, which is basically the force of rotation. How much energy do you get from rotating in a certain direction? How much energy is in that rotation? And that's torque, basically. The more you spin, the more energy you have per rotation. So now he's going to use the power of the spin to give himself a lot of angular momentum to propel him high distance to the rocket. So he's going to use the mass. He's using that ball to increase his mass, which will give him more acceleration and fling him into space. And as you can see, his gravity is decreasing to zero because he is escaping the orbit. And as you escape the orbit of a body in space, you lose your gravitational influence. Now, it's not actually zero. You're always going to be pulled on different forces in space. You know, stars are pulled by quasars. Quasars are pulled by supermassive clusters of galaxies. Those clusters of galaxies are pulled by a black hole singularity. So there's always some gravity acting on you in space, but it's a non-zero. It's not a non-zero amount, but it's a near zero amount. It's so insignificant that when you're out in space by yourself, you basically are in free motion, meaning the only forces immediately acting on you with significant, significant values would be your own force, which means you are your own gravity. You can move yourself and you're not going to be pulled towards anything when you're in space. I mean, you are being pulled. You're in an orbit at all times through bigger masses of gravity. If you look at like space-time diagrams, you'll see that the bigger forces of gravity pull things into it like a hole, like in a flat surface, like a trampoline. It'll be like a big ball, a big metal ball in the middle of the trampoline. It'll curve down, and it'll pull things near it towards it. But for the most part, when you're far away from it, you'll be safe from the forces of gravity. So now he's in anti-gravity. He's not in anti-gravity. He's in basically zero gravity. He's in a zero gravity environment. There you go. Now he has thrust. So that's the angle of thrust. And it's acting this way. Oh, there we go. So we had a formula for thrust too, which is just mass times the thrust over the velocity. So it's just giving him speed towards a certain direction. Something is pushing him away without gravity acting on him. So he's basically getting free acceleration. I mean, reality is he's burning fuel, but in this world, fuel doesn't exist. Energy is free. So now he's heading towards the biggest star in the galaxy. And he's increasing the speed. So here we have the Lorentz factor. So basically this is describing, in a nutshell, it's describing like how far away are you from the speed of light. And what it really describes is the Lorentz factor describes the wavelength of light. And the higher the wavelength, the more energy you have. So right now he's like near zero Lorentz factor, which means he's like barely at the speed of light, which means that to him, light will be as it's meant to be perceived. It will be on a normal wavelength. The wavelength won't change. But as you increase your Lorentz factor, you'll start to see red shift, blue shift, which means that light in front of you will seem compressed and light away from you will seem stretched out. Even though that light is not being stretched out, it just seems like it because you're moving so fast that the light in front of you is like being pressed and the light behind you is being stretched out because you're just going so fast. It seems like the light is getting further away from you. So that will be a measurement basically for how close to the speed of light he's going. So now it's like not even close to zero right now. Here, so we have a unit of measurement for light now. So now we have light, which tells us the unit of measurement for light. Now we're gonna see how light is described in this universe. That's the speed of light. So that's how fast we are compared to the speed of light. That's the wavefront, which is basically the wavelength of the light. Basically, it'll tell us what kind of wavelength it is. That's the normal vector. So basically, the normal vector is a vector perpendicular to a reflection. Basically, it describes the reflection of light. The light will go in at one vector and it'll hit off at an angle perpendicular to its normal vector. So they'll go in like this, and it'll go in at creating like a right angle between the two angles. So that's the normal. Now he's changing the wavelength. Now we have a unit of measurement for what wavelength of light we're dealing with, which will be useful to describe the phase shift in the light as he goes faster and faster. So far, I pretty much understand what's going on here. It's pretty elementary stuff. So now he's going to use the orbit of the planet to give himself a free speed boost. And I like this little angle diagram showing how the orbit of a planet is giving him extra velocity, because it's a very simple formula. It's the next planet will show a much better showcase of this formula in my opinion. So he's going to go for the bigger planet with more gravity, which gives him more acceleration. There we go. So now this is a perfect diagram. You have the U, which is the vector of gravitational pull that is perpendicular to the entry point of the orbit. So he's entering the orbit at this angle, and the U is the angle that he wishes to go at. And basically, his velocity is being multiplied here by the gravitational force of the planet, which is like 40,000 meters per second. That's the gravitational pull of the planet, and he is entering with this much speed. And so basically at this angle, he's going to change his angle every 5 degrees on the delta until eventually he escapes the orbit. When he escapes the orbit, you plug in the initial velocity times double the pull from the planet, the vector of being pulled into the planet, and then you run it through all that math, the cosine, which is just the angle that he's being rotated on the planet's orbit, and then it'll give you that function v of f, which gives you the v final, which is the new speed that he gets, the v final, the v of f. So now he goes at a much higher speed than when he initially entered, thanks to the orbit, the gravitational orbit of the planet. He's using it as a slingshot, basically. There you go. That's slinging him forward. And that's how our satellite Voyager, that's how it's propelling itself through the universe faster and faster. That's how it escaped our solar system, is that it rotated through the bodies of planets in our solar system to basically give it a boost, and that helped it get faster and faster until it escaped out of our solar system. So now he's going to try and use the sun, but the problem with the sun is it's a huge amount of gravity. It's pulling all those planets around it at an orbit, and basically if his angle is not steep enough, if he's going too far into it and he doesn't change his angle, the angle that he's perpendicular to will eventually come closer and closer. So he basically has to keep increasing the angle to create a perpendicular angle that hopefully will escape him out of the orbit. So right now his gravity is going down into the sun. He needs to change his direction to go higher and higher up. So it's like when you throw a ball. You want to throw it further. If you want to throw it further, you have to aim higher up. You can't aim out, because if you throw it straight out, the ball will just fall down faster. So you got to aim up. He's got to aim up to escape the orbit of the sun, and he's just gonna make it, barely gonna make it. And there you go. Now his velocity is massively increased because he's being pulled by the gravity of the sun. And when he finishes his revolution, boom, he just flies right out of the solar system. Huge increase. Now he's almost about to reach a Lorentz factor of 1. 1%. Perfect. So that means he's moving at 1% the speed of light. Now let's keep going and see how far I can get before I start to get confused. A magnet. So now he's going to try and orient himself on a magnetic field. So now we have the formulas describing the magnetic field. And what he's going to do here is he's going to take this rod, and usually all atoms in the universe have like a small magnetic field. There's a weak force and a strong force that acts on atoms, keeping them together. And that magnetic force is what keeps the electrons polarized in a certain way. Protons go up, they're protons, so they're positive, and then electrons are usually negative, they go down. So what he's going to do is he's going to orient these protons and electrons to basically go in the direction they're supposed to. So he's going to orient the atoms, and that'll orient the field in the atoms to point in a certain way. And when you do that for all the atoms in the material, usually a metal material, that will cause it to have a magnetic field, meaning that it will have a positive side and a negative side. So we're going to see that right now. So now we have the magnetic flux. So we have like a magnetic field generator, which is going in this direction. And so now he's going to orient the rod. Yep, as you can see, he's making all the atoms in them point up and down straight. Now he has a magnetic field with all the protons pointing up, and then the electrons pointing down. So now he has oriented atoms. He's going to change the direction of the magnetic field from going up and down to pointing this way. And what that is going to do is basically it's going to make it like a vacuum. So he's going to try and suck himself into the magnetic field of those magnetic flux generators. So because his direction is this way and the positive direction of it is this way, the negative is going to get pulled into the positive, and as it finishes through the positive, the positive is going to get blown away by the negative on the other side. So think of it like a fan. You have the air sucking in from one way and then blowing out the other. It's basically like you're getting sucked into a fan and you're going to get blown out the other way, and it's going to give you acceleration. So the negative is going to get pulled into the positive, and then the positive is going to get pushed away by the negative. Opposites attract, and then opposites, the same kind repel. So now it's being propulsed, and this is basically a rail gun, basically. Although I wouldn't see him getting such an exponential speed increase that quickly in my eyes, just because the railgun, this is what they use in the Large Hadron Collider to accelerate atoms, is they take hydrogen atoms, they give them a magnetic field, and they spin them through basically a giant tube over and over and over with more and more acceleration until they're so fast they're 99% the speed of light, and then they smash them into each other to make them explode into their most fundamental parts. Now he's 80% the speed of light. That's his Lorentz factor. And that curve really there is so cool, because that curve, that C, is basically the limit that matter can get to when it has mass. So this basically is the formula for E equals mc squared. As you approach C, the amount of velocity needed to reach it becomes exponentially, it's like a logarithmic function. It becomes exponentially difficult to reach. To reach C, you're going to need infinite velocity, because your mass is going to be the final limiting factor from you reaching the true speed of light. You're going to need an insane amount of energy to propel yourself at the speed of light. And this would be the energy to split atoms apart. So he's 80% of the speed of light, which is difficult, but not impossible to reach. And he's just blitzing through the rest. Yeah, now we're seeing that phase shift where the wavelength of light, and we're also seeing time dilation, where the wavelength of light seems compressed in front of you and pulled apart behind you. So light behind you will seem kind of like further away, and light in front of you will seem closer. Yeah, that's the Doppler effect. That's the phase shift. Now we're seeing the parts of the galaxy. Now he's approaching the black hole. Yep, that's a black hole where space is compressed into a singularity. And the amount of distance required to cross that space decreases as well. So there's an atom that falls into the black hole. Its phase shifts towards red, and then it disappears forever. And for some reason, he's going to chase that atom, not knowing that when you fall into a black hole, I love this demonstration. Yeah, he gets compressed into a point because the light from him is radiating back less and less until it seems like he's just flattened. But when you go into it, it really is like falling into a hole because the escapable light is decreasing less and less until there is no more light coming out of the black hole. So at that point, I mean, no light escapes the black hole, but to the inside perspective, it seems like the amount of light entering is less and less because it's all being focused into a singular point. So it really does feel like you're falling into a hole. You're getting further and further away from reality. Now he's falling further and further, and now he's at the point of no return. There's no point to even turn on light because at this point, you try to turn on light, right? And you're seeing the atoms in front of you just being pulled into the black hole. You know, there's no way to see what's ahead of you in a black hole because light is being sucked away from you as you enter it. The only thing you can see is the past. You can see the past, but you really can't see the future because there's no light going this way. So you're only seeing stuff going behind you. This is where time is just completely dilated. And this is the crazy part. So when you compress space together, causality, which is like interactions between matter, gets compressed as well, until eventually all matter shares a very close space, which means that events that happen at that wavelength, yeah, so now you're going to see matter being pulled apart to the atom. This is spaghettification, where matter is being stretched, pulled closer and closer, and matter away from it. The distance between matter closer to the black hole and the matter away from the black hole gets way more exponentially bigger. So it seems like point A and point B are getting further apart, even though they're part of the same object. Now it seems like you're atoms away from the apple, even though you were just holding it. That's how big the distance is when you get closer to the center of a black hole. It feels like you're being stretched apart, and it just gets bigger and bigger until you're ripped apart at the molecule. Props to this guy for being able to stay together down to the peak to scale. Now he's at Planck's length, which is like the smallest unit. This is crazy. This part, I feel like I'm lost. I'm just gonna assume what I'm seeing and not try to really give a concise explanation because I honestly don't know what is happening at this point. Yeah, he's reaching Planck's length, and it's just so weird what's going on at this point. You have like a timeline, and it's like a multiverse timeline where it shows like the universe inside of a black hole, this, and then he's traveling along that black hole until he reaches its singularity. And it's theorizing that there's a white hole on the other side of the black hole where matter is expelled from where it's sucked in. And then there's a parallel universe, which is like, I don't even know at that point, like, what is a parallel universe? You know, how do you describe that? So he's basically traveling along the timeline, the black hole timeline. And PBS Spacetime has some great videos explaining the timeline inside of a black hole as you get closer and closer. So now I'm going to explain it. I'm going to spoil what it is because I already saw the video. This is him seeing himself in the future. So as you reach the center of a black hole, space collapses into like one point, which means that time is all existing at the same spot, one place, which means that you can see the future and the past. You can see the future in front of you and the past behind you because they're all existing on the same spot together. It's so weird. I don't know how to really describe it. Most math just breaks down at this point, but basically he can see his future self interacting with his past self. And basically what I'm assuming, man, I don't even know what's going on. What was that formula up ahead? Probability waves. So is that like on the quantum level where we have like wavelengths of like quantum particles and we see what the probabilities they collapse? I have no idea what's being going on here. The potential and kinetic, man, that's crazy. It looks like the formula for quantums right there. That little like trident, that's like the formula for the phase of like a quantum particle. This is way above me. This is way above me. I have no idea what's going on here. I don't even know what these things are. It's like light, basically, like molecules, and this is like information, like numbers. So it's like information theory, like basically saying that everything in the universe is made up of like describable numbers instead of like matter. And that just takes up space, and that's like binary in nature. So he's because time is compressed into a singular point, the past can affect the future. It's really weird to describe, and I don't know how to explain it, but basically, because you can see the future and the past, you can basically travel along that timeline up and down. Realistically, you couldn't, because in a black hole, the force of the black hole exceeds any force that interacts with it. So there's no way to like go up and down a black hole. But if you could, you'd basically be able to go back to the past, because that's light behind you that you entered in from. And then if you want to go back to the future, you can just keep going back down the black hole. Your destination is the same, towards the singularity, which is the white hole that this guy is interacting with here. He's interacting with a white hole. This is the apple that he brought with him into the black hole. He's giving it to his past self. Man, what is that, bro? Cauchy-Meow manifold, compacted dimensions, 6 holes 3. So this is basically like higher spatial dimensions. Why are there higher dimensions within a black hole? I don't know why. That's so weird to me. Again, I would love to see physicists react to this and explain what's going on here. But I know that basically this is like getting into like string theory stuff, which is like saying that we have 11 dimensions in our universe. And, you know, I don't know why there are multiple dimensions in a black hole. Some theorize that a black hole is like a pocket universe. And that's why when you go into a black hole, you can't escape it, because it's expanding faster than the rate at which matter can escape it. So it's basically saying like a black hole is a pocket universe. I have no idea though. Yeah, I think that's just describing the dimensions of the apple. I have no idea, honestly. But it's a hyperbolic shape, basically. The Cauchy manifold. That's like a hyperbolic shape, which is like a non-Euclid shape that has multiple dimensions here. But this is just some crazy. I'm assuming this is a white hole, which is where matter from the black hole gets expelled, or like a wormhole where matter can teleport. And if that's true, that would break the law of not just causality but conversation, basically saying that you can pull matter from anywhere and just disperse new matter into the universe, which just breaks the laws of conservation of mass, which means that entropy just doesn't exist because we have infinite energy to keep wasting. It's just so weird to me. This is just a part of the video that I can't really explain because I have no idea how to describe it. Hyperbolic space. So yeah, this is basically what I was saying. So it's a hyperbolic shape, and our universe is one of those hyperbolic shapes, which isn't fourth dimension. It's not fifth dimension. It's like 11th dimension. And this is Einstein-Rosen bridge. I have no idea what that is, honestly. I have to Google it. A wormhole. There we go. That was what I was thinking. Is this is a wormhole, right? And it is a wormhole from the past. So because this guy who's playing with the wormhole here, he is in the black hole, he can see the past that from the light that came with him. So light is considered the universal constant of information in our physical universe, you know, because it's the fastest form of information. So it describes causality. So when he went into that black hole, he brought his information from the outside universe into the black hole, and now he can see that outside information through the wormhole. And I'm assuming this wormhole is to a different parallel timeline or a different dimension or something, because if you can pull matter from your universe and put new matter into a different universe, that means you're just pulling from like a multiverse. And I don't. If they go into multiverses, I have no idea how to describe that. That'd be crazy. So that's him in the past, basically. This is the future dude. This is the past dude, and this is the dude from the very past. And they can both see him because in their world, they're looking through a parallel timeline, basically. I'm assuming that's what's happening. Is this is a wormhole to a past timeline? Because it would make no sense if you can interact with your own timeline from the future. How would that even work? So he took the rope from wherever, I don't know where this place is. He took the rope from his timeline and put it into the new timeline, which is the past timeline. It's going to fall out that wormhole, which just gives new mass in the universe, breaking the law of conservation, which means that, you can just have matter spontaneously come into existence from nowhere for no reason. And there's how he got the rope, is that this guy from the future influenced his past. And this is somewhat true, is that your past dictates your future and your future is connected to your past. That's causality. What happens in the past will affect the future. There might be randomness in the future, but we don't know for sure. What we do know is if I push a glass of milk on the floor, my action from the past is what caused a glass of milk to be on the floor in the future. So when you want to ask, why is there milk on the floor? It was from something that definitely happened in the past. So him putting string into the beginning of the video is connected to the past because the past is always connected to the future. But how he's just casually interacting and putting new matter into a past timeline, it just kind of breaks mathematics. It just breaks physics at that point. Man, this is weird. One-dimensional open string? What the heck? So he's basically interacting with like just space on the most basic level. This is string theory. That's why he's playing with strings, because we're theorizing string theory, which may or may not be a model for our universe. I have no idea, honestly. A lot of people say no, a lot of people say yes. I don't know, man. But what I do know is we're constantly changing what string theory is, better describe our universe, but we still haven't found out, how it all comes together. So that's how they brought it in the ball. And the string theory is above me. I have no idea how to understand string theory. So they created a rocket from strings. Again, I have no idea how this is all just happening. I just all understand that there's a wormhole to the past, and these guys from the future are just throwing stuff in there like it's a toilet, and they're just flushing it down the toilet. So now he's rotating the wormhole, which somehow changes the timeline and moves things into the future. I think he's changing the direction of the wormhole. It must be like a higher dimensional wormhole, like a fifth dimension wormhole or fourth dimension wormhole. I'm gonna assume it's a fifth dimension wormhole because later in the video he goes to like the 11th dimension or something. So I'm guessing as you rotate the wormhole, it's changing its entry in space time, which means that as you rotate it, it moves ahead in time, meaning that you can change the angle and end up in a different point in the future, or you can rotate it and end up in a different point in space. So that's what I'm assuming. I have no idea what the hyperbolics of this is. This makes no sense to me. Triple Tipler cylinder, solar masses greater than 10, cycles a second, length infinite. So I guess he's just cutting through space-time with this like portal, and he's opening up into a different part of space-time, escaping antiparticle. So he's changing the angle of this fifth dimensional wormhole to go to a different point in space-time. And that's him like even further in the future or something. Yeah. So he's moving his actions. He's moving back in time, basically. He's basically moving back in time to show the past guy, hey, this is your past. This is my past. I'm giving you my past information to you because the past is connected to the future. This is just time travel. I have no idea. He's pulling matter from different parts of whatever. I'm assuming he has access to the multiverse, and he's pulling random planets and galaxies from different multiverses and throwing them into the current timeline, which I don't know how the heck that's happening, bro. That's crazy. I mean, this is all theory at this point. So now he's showing him a new point in space-time. him going into the black hole, which is when he threw the apple in, and that action from the future affected the past. But because the past is always connected to the future, it doesn't matter whether he did this in the future. If it affected the past, it will create the future that he is currently in. You cannot escape the future. So whatever happened in the past will cause the future to happen, which caused him to go into the black hole and then meet his future self. And he's trolling a little bit. Yeah, so he falls in. So I guess these are like, this is the multiverse. That's the only way I can describe it. This is a type 1 universe, and there's like 11 different universes on different dimensions. Like there's 11 different dimensions, each with their own space-time, and I have no idea what the frick this kind of wormhole is. So that's a type 11, and he took the hat, and he's gonna go into the new parallel multiverse, whatever, because he's the future. So he will always be ahead of the past, which means even though he can interact with his past, I don't know how to explain it. Like his past and the future are connected, but the past guy will not have any idea what will happen in the future. But the future guy already knows what will happen in the past, and he's interacting with his past to create his future. It's paradoxical, I know, but somehow it makes sense. I don't know. So he's going into a parallel dimension. He's escaping our timeline and going into a completely different multiverse, and he's just traveling the multiverse like Thanos with the Infinity Gauntlet. He's just jumping timelines, and I have no idea what's going on. But he's going to a completely different reality. So that's the video. I tried to understand it as best as I could. I hope that we get some physicists with an actual, science background to, further explain the video, and hopefully give insight to what happened at the very end, because I was a little bit lost at the end. But if you like the video, share it, leave a comment, or not, I don't really care, but I just wanted to see how much I could understand. If you have criticisms, I'd love to see some corrections, because I have no physics background, but I'm just going off of my general knowledge from what little I know from some undergrad physics courses and mathematics courses that I took. So yeah, thanks for watching. I don't know. How do I stop this video? Figure out how to stop the video.